Good morning, sir.
Good morning, good morning.
Good morning, sir.
Good morning. Good morning to all.
Good
Now
morning.
the student
Good
types
morning,
that
sir.
we have covered inductors in parallel. I generally cover if I have missed in any batch, please have a look at it. It's a very small thing. Two inductors in series. Two inductors in series. L equivalent is equal to L1 plus L2. Very orthodoxy, you will write plus or minus 2M. If the current is in the same sense in both of them, it will be plus 2M. Now, mutual inductance also taken into consideration. If not, it is only L1 plus L2. Two inductors in parallel. Don't use mutual inductance here. 1 by L equivalent is 1 by L1 plus 1 by L2. Second, if two inductors are in series and you have a resistor, you have one inductor and two resistances in series, R1 plus R. Initial current in this was I naught. So what was the initial energy? Half L I naught square. Right? What amount of energy is lost through this and what amount of energy is lost through this? Heat here is directly proportional to I square. Directly proportional to I square R. Whether I is the same, so I will remove I square. So half Li naught square is split between these two in dissipation in the ratio R1 by R1 plus R2 into half Li naught square. Here R2 by R1 plus R2 into half Li naught square. On the contrary, if I have got one inductor and two resistances in parallel, R1, R2, L. Here delta H is inversely proportional to R. V square by R. V square by R potential is constant. Right? So here delta H1 will be R2 divided by R1 plus R2 into half Li naught. Delta H2 R1 divided by R1 plus R2 into half Li naught. They are hitting regularly on these two formulas, time and again. Heat dissipated in this, heat dissipated in this. Here, heat through R1 will be R1 by R1 plus R. Here, the heat through R1 will be R2 divided by R1 plus R. If I have forgotten in any batch, please make a note of it. Can I rub the board?
Yes, sir.
Before I proceed with communications, one small problem which generally I cover in the class, which I have not done in any of the batches. Have a look. Here I have a capacitor. Here I have a capacitor. In 2 minutes, I'll start communication. Till then, solve this problem. Current in the inner loop changes as I is equal to 2t square. Find the current in the capacitor as a function of time. Find the current in the capacitor as a function of time. This is given as A, this is given as B. Current in the inner loop is I equal to 2t square. Find the current in the capacitor as a function of time. Find current in capacitor as a function of time. Your given B is much greater than A. Your given B is much greater than A.
Sir, there should be resistance in the outer loop.
Outer loop resistance is R. Outer loop resistance is R. Induced EMF in the outer loop. Have a look at it. Induced EMF in outer loop will be equal to M di by dt. Induced EMF in the outer loop is coefficient of mutual inductance between the two into rate of change of current in the first loop. This is outer loop. Mutual inductance तभी scene में आएगा when you take current or rate of change of current in one and EMF in the other. This is induced EMF in the outer loop. This is in the inner loop. If they were in the same loop, what would this symbol be?
L.
L, self-inductance होता है. Right?
Yes, sir.
Fine. People are typing the answers. Please type to the host, not the co-host. Co-host is my cell phone. The message comes and disappears. right? Dhanay, your answer is correct. Now, if you can tell me capital M, my job is done. How do I take capital M? I do the reverse. Capital M के लिए M12 is equal to M21. I am not in a position to take current and find out the flux through the outer loop. I am not, unless the magnetic field is constant here. You give me a circular loop and a uniform magnetic field, but smartly I can find out the induced EMF in the outer loop. This is a solenoid. Induced EMF in the outer loop is quite easy. But this is not. So because of this current, finding out the flux through the outer is very difficult, because magnetic lines of force start from here, go inside, start from here, go inside, start from here, go inside. I don't know the magnetic field here. I know only the magnetic field here. So because of this current, directly finding out the EMF in the outer loop is not possible in this case. In this case, how is it possible? My magnetic field is because of a solenoid. It is constant. So getting the induced EMF in the outer loop is much easier. This point, is it clear to all?
Yes, sir.
Yes, sir.
So hence, you will use the concept of reciprocity theorem. Now I'll assume current in the outer loop. If I assume if I is the current in outer loop, flux through the inner will be mu naught I by 2b into pi a square. Because of this approximation. If the approximation would have been given, I am again in trouble. Now flux through the inner upon current in the outer loop will be mu naught pi a square by 2. This is coefficient of mutual inductance. Now substitute here EMF in the outer will be equal to mu naught pi a square by 2b into di by dt. I is given a function of what? D by dt of 2t square. Once I have this outer loop may, I have a battery of this EMF, capacitor and a resistor. Finding out charge on this is q naught into 1 minus e to the power minus t by tau. Several chapters are combined in one problem, and a good one. Best part of this problem is learning how to use mutual inductance. He gave you current here. He asked you induced EMF in it. Directly, I am not in a position to calculate. But if you would have given me a solenoid like this perpendicular to the board, I'll do it very easily. Because magnetic field is constant there. E is d phi by dt. Here, the concept of mutual inductance, assuming current in the outer one, finding out the flux through the inner one, and getting mutual inductance, thereby using reciprocity theorem, is the catch in the problem. Once you get Q, finding out current is dq by dt. All of you need to understand this. communications. Much of this is information for the sake of information, but it will be equally important for your HSC as well. First of all, we start with a flow chart. This is called information system. Technically, in electronics, these are called block diagrams. From the information system, you send the message signal to what? To the transmitter, right? Transmitter sends through the channel to the receiver. I am running short of space there, so I will draw the next part here, but technically it will come in the same line. Receiver gives the message signal to user of information. Message signal to user of information. This is the user, this is the information source. All of this will be put in one block diagram. Did you people ever see the motherboard of the computer or even TV sets nowadays? If they open any part, there will be individual plates. Each plate there will be n number of transistors, diodes, all the components should. कौन सा component खराब है हमें पता भी नहीं चलेगा. That plate as it is have to be changed. In this you have a problem, whole of this will be changed. It becomes easier for the manufacturer to deal with that. Right? Message signal में how do you convert? Using a transducer. Sound pulse converted into an electrical pulse. What will the transducer do? It converts a signal into a format which can be transmitted. I talk. Cell phone, first of all, converts my signal into an electrical pulse. That is what is called a transducer. Then it sends it to the transmitter in the cell phone itself. Cell phone transmits it using the channel which is called the communication. That goes to the receiver. It will be refined and given to the user of information. Channel may be wires, cables, or wireless. Channel is the means of communication. Take down the diagram, 1 or 2 definitions I have to explain.
Sir, could you just re-explain the transducer part?
I will dictate that. I will dictate the point. Take it down, please. Tell me when I can dictate.
Yes, sir.
One second.
So what is that word under message signal?
Transducer, Trans. Transducer, Trans. Write down the definition of transducer. Transducer converts a non-electrical signal. Transducer converts a non-electrical signal into an electrical signal. Transducer converts a non-electrical signal into an electrical signal. Second point. Transmitter converts the message signal into a form suitable for transmission.
Sir, can
Through
you
the channel. Suitable for transmission through the channel.
Sir, can you repeat transmitters?
Transmitter converts the message signal into a form suitable for transmission. Transmitter converts the message signal into a form suitable for transmission. Now listen, if ever there is noise disturbance in the signal, it is neither because of transmitter nor receiver. It is because of the channel. Whatever noise is incorporated, it is because of the channel. Noise gets incorporated only in the channel, in the means of transport of communication. It may be wires, it may be cables, it may be wireless. Whenever there is noise in the signal, it is because of the channel. Note, noise in the signal is due to disturbance in the channel. Can I rub the board?
Yes, sir.
Yes, sir.
Sir, just for wires, cables, and
Wireless.
oh, okay, sir.
Wires, cables, and wireless. Now, there are two types of transmissions, point to point. Point to point. I call up a person and I talk to him. I and he will be able to hear. So it is called point to point. single transmitter and single receiver. This is single transmitter and single receiver. Single transmitter, single receiver. The other is broadcast. The other is broadcast. Single transmitter and multiple receivers. Broadcast, you will not have a control on who is hearing it. FM radio 91.1. They are single transmitters, multiple receivers. Anybody traveling in the car can hear. Anybody traveling in the car can hear. 1 second. Gautam Dada, sir, are there no CTs this week? Right? अभी CTs के बारे में सोच नहीं रहा. CTs है तो है, नहीं है तो नहीं है. अब ऐसा डाउट मत टाइप किया करो. स्पैमर तो नहीं है बच्चा. बहुत दिनों के बाद स्पैमर्स की याद आ रहा है. Single transmitter and multiple receiver. You do not have a check on who is hearing to you. Radio frequencies are transmitted. TV signal is transmitted. Anybody who has a receiver can see the TV. On the move, inside the house, outside the house, kahin par bhi dekh sakte. Right? Now, one tricky part in this question is the only one thing that comes. See, here I can recognize any example you give me. It is broadcast. Broadcast is you're sending the signal. Anybody with a receiver anywhere who has access to signal will be able to receive. Right? Single transmitter, single receiver. Now we'll have a control on who is receiving it. Now the one which comes in between, which doesn't come into these definitions. These definitions were made long back. Now present developments are, you can have a conference call. But in conference call, even Zoom for instance, it is multiple receivers, but I have a control on who will receive the signal. I can cut anybody at any stage. The person transmitting has access or control on that. That falls yet in this category only. Till when? It is a Zoom call, Zoom meeting, it is a conference call. I can add anyone or remove anyone. So when the receiver has a control, or when the transmitter has a control on the receiver who gets the signal, it is yet point to point. Maybe I have multiple points, but the points are defined and in the control of the transmitter. Is this clarification clear?
Yes,
sir.
sir.
Can I rub the board?
Yes.
Yes, sir.
Now, signals which are transmitted are of two types. Signals which are transmitted are of two types. One is analog, the other is digital. Analog, continuous variation of voltage and current. Analog will be continuous variation of voltage and current. Essentially, it is essentially single valued function of time. This is a discrete. Analog and digital. Digital is discrete, stepwise value. Discrete, stepwise value. And generally, this is a binary system. Above that voltage signal is 1, below that voltage signal is 0.
So what does that essentially signal value?
One for a particular value of time, I'll have only one value. At a particular value
Okay,
of
okay.
time, I'll have only one value. Need not be multiple values.
Okay.
Write down two definitions. Amplification. ये boards में definition as it is लिखना है. याद रखो. Amplification, process of increasing the amplitude process of increasing the amplitude process of increasing the amplitude using a device called amplifier using a device called amplifier bracket necessarily to compensate the attenuation of the signal necessarily to compensate the attenuation of the signal.
Can you repeat the entire thing once again?
Process of increasing the amplitude. Process of increasing the amplitude. Using a device called amplifier. Necessarily to compensate the attenuation of the signal.
Yes, thank you.
Full stop. Then the question is, what is attenuation of the signal? Write
Yeah.
down that attenuation is the loss of strength of a signal. Attenuation is the loss of strength of a signal. Attenuation is the loss of strength of a signal while propagating through a medium. Attenuation is the loss of strength of a signal while propagating through a medium. Now, in this chapter, we define bandwidth as the frequency range in which the equipment operates. But I taught you what is bandwidth in LCR circuits. AC circuits में half power बताए कि नहीं?
Yes, sir.
AC circuits में half power. This was the graph for I naught. This is
Yeah.
I naught maximum. Half power. This will be omega 1. This will be omega 2. This is I naught maximum by root. At I naught maximum by root 2, this will be half power frequencies. Half power frequencies. So bandwidth delta W is omega 2 minus omega. Right?
Omega.
2 minus omega 1. AC circuits may half power frequencies I have taught. Do you people remember this?
Yes.
This is bandwidth. In this chapter, we define bandwidth as the frequency range over which the equipment operates. And what is that frequency range? Half power frequencies. What is half power? This will be half the power of the maximum power dissipated. half the power of maximum power dissipated. They are called half power frequencies.
Sir, what is written at the I naught at the top? I naught.
Suffix M. I naught suffix M. Suffix M. Maximum. Maximum value of I
Okay,
naught.
sir.
Maximum value of I naught. I naught is the amplitude. At resonance, you will have the maximum value of I naught. That is the omega R. And what is the value of omega R? Omega R is 1 by
root LC.
LC. Don't forget these things. ये AC में डिराइव किया ना यार, यहाँ भी एप्लीकेबल होगा. यस, यहाँ भी एप्लीकेबल होगा. One more definition. Repeater.
तो बैंडविड्थ का लिखना क्या था डेफिनेशन?
Pardon?
बैंडविड्थ का लिखना क्या था डेफिनेशन?
Frequency range over which the circuit operates.
Okay.
Frequency range over which the circuit operates. Frequency range over which the circuit operates. One more definition, repeater. Write down the definition. Repeater. It picks up a signal from a transmitter. Repeater. It picks up a signal from the transmitter. It picks up a signal from the transmitter, amplifies, picks up a signal from a transmitter, amplifies, and retransmits it, to the receiver.
So it picks up a signal from the transmitter and
It picks up a signal from the transmitter, amplifies, and retransmits it to the receiver. Sometimes with a change in the carrier frequency. Sometimes with a change in the carrier frequency.
Sir, could you just repeat sometimes?
With a change in the carrier frequency. Sometimes with a change in the carrier frequency. The best example for a receiver is communication satellite. The best example for a receiver is communication satellite.
So you mean repeater?
Yeah. It picks up the signal, retransmits it to the receiver, communication satellite. You send the signal to the satellite. It will change the frequency of the carrier wave and it will retransmit it to the receiver. So it is not just transmitting, it can even change the frequency. That is called a repeat.
So can you dictate the bandwidth ka definition once again?
Bandwidth, frequency range over which an equipment operates.
Thank you, sir.
The value of the bandwidth will be half power frequencies. Omega 2 minus omega 1, they refer to half power, half the maximum power. Few values you have to remember. Standard AM. What does AM stand for? Amplitude modulation, which nowadays is not in use. Our childhood radio me, there used to be only three, and shortwave 1, shortwave 2, medium wave. Then the transmission was based on amplitude modulation, right? This is almost outdated, but standard amplitude modulation transmission was done between 540 to 1600 kilohertz. 540 to 1600 kilohertz. FM broadcast is at 88 to 108 megahertz. अब समझ में आया what is FM 91.1, FM 91.8, FM 98.2, 104 point something, whatever is that is the frequency at which they are transmitting their signal.
So what's the full form of FM?
Frequency modulation. This is amplitude modulation, this is frequency modulation. TV signals 54 to 72 megahertz is very high frequencies. 76 to 88 megahertz is the actual TV transmission signal. 174 to 216 megahertz is ultra high frequencies. 420 to 890 megahertz is again TV signal. Cell to mobile 896 to 901 megahertz. Cell mobile radio. Cell mobile radio.
Sir, what is VHF?
What is?
VHF?
Very high frequency, ultra high frequency. Tell me when I can rub the board.
So और कल डेट नहीं आया.
Let's pray that it is in March.
It's
But tayari jari rakho. Don't be overconfident or don't postpone things.
इससे ज्यादा अजीबोगरीब बात.
Now listen, the main part here is about transmission. Right? Listen to it. Ground wave, propagation of EM waves. Propagation of EM waves. There are three types of propagation. Are you able to see this part of the board? First is ground wave. First is ground wave. How is ground wave propagated? It is propagation through surface wave. This is, I'll put it this way. This is called, mode of propagation is called surface wave. Mode of propagation is called surface wave. What do you mean by surface wave? The wave glides over the surface of Earth. Wave glides over surface of Earth. Right? This is called a surface wave. One problem with this, you will have to radiate signal with high frequency. Radiate signal must be high frequency. This is one problem. Second problem is a much more bigger issue. Antenna should be comparable to the size of the wavelength. Antenna should be comparable to wavelength, at least lambda by 4. Now this is the problem here. Antenna should be comparable to the wavelength. I'll show you the values. Antenna, if you people have ever gone for long drives and old transmitting towers, if you people see, they will be approximately at the height of 500 meters. Right? Why? I'll give you an example. Have a look at this. Suppose, example for this, I'll come to that again. Have a look at the example for this. Generally, you can hear to signals of 20 hertz to 20 kilohertz. Let me take the frequencies 20 kilohertz. You're transmitting this close to 20 kilohertz. If I send the sound signal as it is, radio want to transmit the sound signal as it is. It cannot have a frequency greater than 20 kilohertz. Then I'll not be able to hear. Your audible frequencies are 20 hertz to 20,000 hertz, right?
Yes.
Yes. Yes, sir.
Now, this should be a, please stop typing messages on the host. कोई कुछ भी टाइप करते जा रहा है, stop typing messages which are not relevant to the class. अगर नहीं सुनना है तो disconnect कर दो. आपको chatting करना है, this is not the platform. क्वेश्चंस पूछते जा रहे हो, क्या क्वेश्चंस है यार, कौन क्या सोचता है, मैं उसके बारे में थोड़ी बता पाऊँ. And this guy is continuously typing. When are the revision lectures starting? You type once again, I'll remove you from the meeting. आपको communications पढ़ना है कि नहीं? Now, maximum frequency is 20 kilohertz. Now, if I send this 20 kilohertz as it is, the wavelength of this is 15 kilometers. How did you calculate here? Speed of the electromagnetic wave is n into lambda. Substitute and see, you are getting wavelength 15 kilometers. Right? Agreed?
Yes.
Now, 15 kilometers range का antenna थोड़ी construct कर पाओगे, नहीं कर पाओगे. So suppose I tell you the signal is 1 megahertz. Signal is of strength 1 megahertz. Then what will be the wavelength? 300 meters. अब lambda by 450 meters का antenna तो construct कर पाऊंगा. Right? So I can transmit the signal when the frequency is high. So now the critical catch is utna frequency I will not be able to hear. You place it inside another wave and you transmit. Your signal is one wave. Transmission signal has a very high frequency. So what actually happens is, this will be the wave I want to transmit. This will be the carrier wave. Carrier wave will have very high frequency. Are you able to see that? So the transmission becomes easy. This is the way you modulate a wave. This is called amplitude modulation. आपको ये signal send करना है. This will be the signal I use as a carrier wave. This carries the original signal. And this signal will have very high frequency. Very high frequencies can be transmitted and received easily. Is this point clear?
Yes.
Yes.
First, to take this down, we'll further dig into it.
Why should the antenna be comparable to?
That is a requirement. If not, it cannot receive the signals. The derivation, if you take electronics and communications, maybe you will do that. I have not seen the derivation till date. But in electronics and communication, you will have it.
Sir, what's the last point?
Antenna should be comparable to the wavelength, at least lambda by 4. It is not the outer wave is carrying the inner wave. Inner wave is carrying the outer wave. This is my signal. This is my modulation. This is the carrier wave. Carrier wave has very high frequency. Tell me when I can rub the board. Now, the second means of propagation is sky wave. Generally, I
So we-
formulate all of that on one board. Here only the first I could write. Second sky wave will come here. The third will come here. But then I'll have to rub this and write the second. Can I rub the board?
Yes, sir.
No, listen. Sky waves. इस पर बहुत सारे क्वेश्चंस आ रहे हैं repeatedly they are asking questions on this. Firstly, sky waves, few megahertz. First point, I can transmit signals of a few megahertz. Preferably, frequency should be less than 30 megahertz. First point. Sky waves transmission can be done with a frequency lesser than 30 megahertz. What is the principle? What did you tell me ground waves were? Ground waves basic principle was propagation through surface waves. That means waves glide over the surface. Surface of Earth. Waves glide over the surface of Earth. They get reflected. Suppose previous situation I have an antenna like this. Waves glide this way over the surface of Earth. Right? Now here what happens? You are using ionospheric reflection. You are using ionospheric reflection. Earth's atmosphere, troposphere, stratosphere, ionosphere, exosphere. Geography में पढ़ा है ना यार. Right? Now here what happens is this is the ionosphere. Signal is sent, total internal reflection happens, and this is a total internal reflection at ionosphere happens and you receive the signal. Then why can you transmit only frequencies lesser than 30 megahertz? Because frequency greater than 30 megahertz penetrate through the ionosphere and gets lost to the outer space. It will not be reflected back. Hence, I must have frequencies lesser than 30 megahertz. These are basically short wave broadcast services. Ask any of your parents, they will be knowing this in their childhood. The radio signals, there were only three: short wave 1, short wave 2, medium. It is that short wave that we are referring to. Nowadays, there is no transmission based on it. Everything is FM frequencies.
So class is till 10:30 now.
I think. Why did you get that out? You have an appointment at 10:30.
No sir, charge करना है.
क्या charge
मतलब
करना?
टैबलेट चार्ज करना है इसलिए.
Charge कर लो to be on the safe side.
Yes sir.
Yeah, somebody typed TV dish is considered to an antenna. Yes, TV dish antenna works on the principle of taking the signals directly from the satellite. What happens for a TV dish is it's a concave shaped structure. Concave shaped structure. A dish antenna will be like this. Right? At the focus, you will have the receiver. From the satellite, parallel signals are received this way. The signals which fall on are focused at the focus, and you have for the TV dish antenna, you can see the receiver placed at the focus. So parallel light rays converge at the focus. The best example is TV dish antenna. ISPER, they have given you repeatedly questions. They're asking you some frequency. Can this be used for ionospheric reflection? Can this be used for skywave transmission? Verify if the frequency is lesser than or equal to 30 megahertz. Go ahead with the answer. If it is greater than, you cannot use this for transmission through skywaves.
Sir, sir, the frequency should have a lower bound to it as well, right? Because the layers below ionosphere, it should penetrate them.
That dies due to attenuation. Frequency is lesser than 10 megahertz will die due to attenuation. But you can transmit it through skywaves. They will be reflected. But the signal strength goes down. Not that you cannot transmit it.
Okay, sir.
Short wave broadcast services. During our childhood, we used to have this radio stations working on only three: shortwave 1, shortwave 2, medium wave. Shortwave transmissions were done through this. Can I rub the board?
Yes sir.
Space wave. Space wave. What do you mean by space wave? This is height of the transmitting antenna. This is the height of the receiving antenna. If this height becomes smaller, you will not receive the signal anymore. So if this is the Earth's surface. So this has a range beyond which you will not be able to transfer any amount. This will be dt. This will be called dm, the total distance between the two. dt will be root over of 2r into ht, height of the transmitting antenna, where r is the radius of the Earth. R is the radius of Earth. HT is the height of the transmitting antenna. Right? This is called, DT is called, it has a typical name. Listen carefully. Radio horizon. Radio horizon of the transmitting antenna. Transmitting antenna. This is called the radio horizon. dm will be root over of 2rht plus root over of 2rhr. dm will be root over of 2rht plus root over of 2RHR. Direct questions based on this formula and this formula have been asked right from JEE mains till your HSC syllabus.
Sir, one second.
So wait,
Explain the difference between HT and HR. I didn't get it.
HT is the height of the transmitting antenna, HR is the height of the receiving antenna.
Acha, acha.
So what was DM का full form?
DR का कुछ नहीं है, DR कहाँ पर है?
Sir,
DM
DM.
DM का कुछ नामकरण नहीं किया उन लोगों ने.
Okay.
Just a second, sir.
So what is that word after transmitting?
Antenna. ANTENNA.
Will be only asked for this limiting case.
Pardon?
सिर्फ limiting case के questions रहेंगे, right? Where the height is just enough.
The definition of DT and DM will come for the limiting case.
Okay, okay. Thank you.
Suppose if you are able to transmit something like this, right, then you don't define that as DT. DT is when you are just touching the surface. Right?
Okay, sir. Thank you.
Two general formula questions on which they are asking questions. Power radiated, this has got nothing to do with space wave in general. Power radiated is directly proportional to 1 by lambda whole square. Keep this in mind. For a good transmitter, first point you need to have high power for transmission and hence high frequency. Now see the mathematics part of this. Can I rub the board?
so wait.
Yes, sir.
Now, amplitude modulation. This is outdated as on date. It's not much in use. Previously, it was in use, but the basic theory and the mathematics of it goes this way. This is a carrier wave. CT will be AC sine of omega t plus phi. Sine of omega t, omega c t, carrier wave. This is called the carrier wave. This carries your signal. Where will it carry? Inside the amplitude, not inside the frequency. When you do it inside the frequency, it is called frequency modulation. If it is carrying inside the amplitude, it will be called amplitude modulation. How do they do that? This will be AC plus, in the place of AC, you will have even AM sine of omega nt. This is the signal that you are transmitting, and this will be sine of omega c into t. The sine omega c into t I kept as it is. In the amplitude, you have kept the signal which you are supposed to send. Now what you do is you bring AC outside. 1 plus AM by AC sine of omega m into t, sine of omega c into t. AC 1 plus. This is called mu, not coefficient of friction, not refractive index, not dipole moment, but use the same symbol. It is called modulation index. Mu is called modulation index. Mu is called modulation index. Sine of omega c into t. Right? Now, modulation index ka one important parameter. Mu is less than or equal to 1 is a must to avoid distortion. To avoid distortion. Right. Now observe this. We will open up this particular bracket. This will be AC sine of omega c into t plus of mu AC by 2. Mu AC by 2. What I have done, I multiplied the denominator by 2. Numerator will have 2 sine A sine B. 2 sine A sine B cos of omega c minus omega m into t. Is it clear? Minus mu AC by 2 cos of omega c plus omega m into t. What have I done? I used the formula 2 sine A sine B cos A minus B minus cos A plus B. Fine with that? No, here I'll draw the graph for this. Is this part of the board visible? This will be omega. Basically, you are taking the amplitude. Here, frequency. This will correspond to AC. This will be omega c plus omega m, omega c minus omega m. Any wave between these two frequencies will be absorbed by the receiver. This will be mu AC by 2. Mu AC by 2. This is mu AC by 2, mu AC by 2. That's what you have put here. Omega c minus omega m, omega c plus omega m. Effectively, between these frequencies, the receiver will be able to receive. Take it down till here. One small information to be given, and that completes this chapter.
Sir, but what is omega m?
The frequency, omega is the 2 pi n. Carrier wave का एक frequency है. The modulated wave का एक frequency. The wave which is being sent is omega n. Wave which is carrying is omega c.
So the information is actually stored in omega m, right?
The information is stored in the carrier wave. This is the signal, complete signal, which after going to the receiver, the remaining is removed and this is taken.
Yes.
So could you tilt the camera slightly? थोड़ा सा उस side graph. हाँ, perfect.
So this chapter is not there in advance, right?
No. Somebody is typing, do we read NCRT? Please read your HSC. HSC textbook पढ़ो इस chapter के लिए, NCRT नहीं.
Sir, we don't have this in our HSC.
कुछ भी है. Last year था, इस साल निकाल दिया क्या?
नहीं सर,
हाँ सर, मैं मुझे भी नहीं
11th grade textbook, I think.
क्या 11th textbook में है?
Semiconductors is there in the 11th standard textbook.
Sir, 12th के textbook में communication नहीं है.
नहीं है. So
11th में है, just
और
before
chapter
semiconductors. 11th के textbook में है.
Then read from NCRT. Then use NCRT only. So pathetic. They put this in 11th syllabus. हद कर लिया.
Sir, waves 12th में पढ़ा.
Waves 12th में पढ़ रहे हो और ये 11th में पढ़ोगे. I told you I'll show you the photos of the hysteresis loop which we worked on. This was the hysteresis loop ka photo taken on a CROs by professional photographers. The sample was lead barium niobate with lanthanum doped to 0.04. So this behaved as a good permanent magnet. Bad permanent magnet.
Wow.
Very bad permanent. Right? Literally retentivity is 0. Reasonably good. The difference between this and this is this hand is holding a sample of lanthanum doped 0.06 and this is 0.04. Lanthanum when changed by 0.06 and 0.04, magnetic properties changed by this proportion. Strange, right?
Yes, sir.
Yes, sir.
Distorted. Right?
What are the strengths of the magnets? Like, are they like the standard bar magnet strength or much more?
Capital M we will calculate again. It will not be much more. It will be much lesser. Because these are dielectric materials. They show very poor magnetic properties. What made my research work popular then was dielectric materials which doesn't show good magnetic properties incidentally showed abnormally good properties when lanthanum was 0.04 to 0.06. We doped from lanthanum 0.1, 0.01 to 0.08. In between, suddenly it showed a peak. Only for this proportion. This was verified and cross-verified, and it turned out to be so. Hence, that was patented. Scanning electron micrograph. I told you, if you take a photograph of a scanning electron micrograph, you will get the lattice structures inside. Right? Scanning electron micrograph जिस composition पर मैंने काम किया, उसका scanning electron micrograph का photo, the inner lattice structure of the material can be seen. We'll have to identify by the size which molecule belongs to which of them. The amplification factor is given here. Right, scanning electron micrograph gives you the photo of the material inside every damn material. So clearly you can see what is there inside that material.
Do we have to remember this graph and the expression?
This is must. इस पर questions आ रहे. They are asking you the frequency range, this range, between which this will be mu AC by 2. They are asking you the value of mu. Mu is AM by AC. About this, and about this questions are coming.
Yes.
One more important information on which they asked. Somebody was asking any specific reason why you selected lanthanum. It was that those days that was what was done in our lab, so we followed it. No specific reason. Right. One last information in this chapter: maximum modulated frequency. Maximum modulated frequency. Maximum modulated frequency, they have asked more than once. Mu is 1 by 2 pi C into R. Mu into C into R. 2 pi mu into C into R. Right? Do I need to memorize that? Yes, you need to memorize. That completes communication.
So what was the long form FM?
What was?
आपने बोला था ना AM and FM. AM was
Field
field
modulation.
modulation and FM was
FM is frequency modulation.
okay, sir.
So what is C and R over here?
What is C?
And R.
Capacitance and resistance of the LCR circuit.
Acha. Okay, sir. Thank you.
So, can you tell for which chapters we read NCRT and for which chapter should we read HSC?
No. The final lab that we gave you people, summary in front given is from NCR. Final lab का summary पढ़ लो. अगर summary में हर point समझ में आ गया, NCRT did a very good job with the summary. They didn't miss even one point. Summary समझ में आ गया, तो आपको detail में NCRT उस chapter के लिए पढ़ने की जरूरत है. In general. But suppose in the summary you have got some doubts, you will have to refer to NCRT. But those chapters which are only mains topics, communication, semiconductors, diffraction, polarization, optical instruments. Communication, semiconductors, diffraction, polarization, optical instruments. Then why are you not telling me about classical magnetism? Classical magnetism follow HC. The experimental part is described properly in HCV, not in NC. Classical magnetism. Hence, communication, semiconductors, diffraction, polarization, and optical instruments from
NCRT.
NCR. My watch says it is 9 o'clock. You have 15 minutes of a break, and after the break, I'll first deal with polarization, then diffraction. Is that clear?
Sir, will you please discuss diffraction first?
Somebody typed polarization is not done in our batch. So first I thought polarization.
In diffraction, you will do single slit diffraction.
You have only single slit, double slit hai kya?
So
Okay.
actually we have done singles that.
डबल स्लिट आपका सिलेबस में है नहीं फ्रानहोफर फ्रेस्नेल डिफ्रैक्शन सिंगल स्लिट डिफ्रैक्शन ही है right so you have 15 minutes of a break the host will remain connected the co-host will disconnect
Bye, guys.
Polarization.
It gets through fine that way, but this way, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
Firstly, did you people understand what a polarizer is?
Yes,
Yes,
sir.
sir.
Yes, sir.
First point, note, Liko. Sensation of visibility. Your eye senses light. This sensation is because of the electric field of the polarizer. Sensation of visibility. Likho. Sensation of visibility due to light. Sensation of visibility due to light is considered to be produced by electric field component of the wave. Electric field component of the wave.
The electric field of the component of
The wave. So in an electromagnetic wave, electric and magnetic field does exist. Your sensation in the eye is because of the electric field component. It seems your eye is not sensitive to the magnetic field component. Don't ask me why. That's the information given. Right? Next point. Restricting the oscillations of
So what?
field, restricting the oscillations of field vectors in a light wave. Restricting the oscillations of the field vector in a light wave only in one plane is called polarization of light. This is unpolarized. It is vibrating in this direction as well as this direction. Dot tells me perpendicular to the board, in the plane of the board. Right? Polarized light could either be this way or this way. Both of them are polarized in different planes. Polarized light. This is polarized in this direction. That means this direction is restricted. Here it is only this direction. That means this direction is restricted. Restricting the vibration in one direction is polarization. You can polarize only transverse waves. Longitudinal waves you cannot. Take a slit, send light. Light of the dimension of the slit alone will go. But take a slit, keep it in front and talk. Everything that I talk will go to the other side with a lesser intensity. So longitudinal waves are not polarized. Only transverse waves are polarized. That is very important. Please make a note of it. Longitudinal waves are not polarized. Akshat, you're asking for first point. I don't know what is the first point. You mean electric field?
So sensation of visibility due to light is considered to be produced by electric field component of the wave.
Right. Sensation of visibility due to light is considered to be produced by the electric field component of the wave. In the wave, electric and magnetic fields does exist, electromagnetic field. Your eye senses the electromagnetic field due to the electric field component. Your eye is sensitive to the electric field component. Can I rub the board?
Yes, sir.
Repeat the last point, longitudinal waves.
Cannot be polarized. Only transverse waves can be polarized. So there are three ways of polarizing. These three ways completes this topic. That's the beauty. But all three ways you'll have to learn. All three per questions are both for HSC as well as JEE Mains. First is polarizing by reflection. Polarization by reflection. On reflection, it gets polarized. This is something that they observe. Now, this was the wave which is to be reflected. You have unpolarized light falling on this plane reflecting surface. This is unpolarized light. Now, when it is reflected, you get partially polarized light. This is partially polarized light. Partially, it is partially polarized. Right? Now this, what level of the extent of this is polarized will depend upon the angle of incidence. It depends on angle of incidence and mu. Level of polarization. Level of polarization will depend on mu and angle of incidence. This angle of incidence and the refractive index of this material. Mirror का क्या refractive index बता रहे हो यार? Problem is, for a normal slab also, some part will be reflected, some part will be refracted. So that partial reflection is what you are referring to. Now, are you trying to tell me changing angle of incidence changes the extent to which light is polarized? Changing angle of incidence changes the extent to which light is polarized. Tell me when I can rub the board.
Yes, sir.
Can I rub the board?
2 minutes.
Somebody is writing, but on a metal surface. See, just as you don't have a perfect refractor, you don't have a perfect reflector also. कितना भी fine polished surface कर लो, 99.9% can be reflected, 0.1% will be transmitted. Pure metal surface, अब बाहर रख लो, why does it develop heat? थोड़ी देर के बाद गर्म लगेगा, because it absorbs some heat. And where did this heat come from? Electromagnetic. कितना भी आप ले लो, perfect reflector may reach 99.9%. 100% reflector, 100% refractors not available. One more important parameter here. Observe this, number of dots are more than number of these lines. On reflection, what direction of polarization will exist? That direction of the field vector parallel to the reflecting surface. That direction of the field vector, see, this will not be parallel to the reflecting surface, but the dot will be parallel to the reflecting surface. So on reflection, only dots will be left. If I can achieve 100% polarization, I'll be left with dots. Kya matlab? That direction of polarization, that direction of the field vector, which is parallel to the reflecting surface. After polarization, the light gets polarized such that the field vector parallel to the reflecting surface will survive. Field vector parallel to the reflecting surface will survive. Field vector parallel to the reflecting surface will survive.
Sir, can you please
repeat the
repeat?
point?
The field vector parallel to the reflecting surface. On reflection, field vector parallel to the reflecting surface will survive. Yes, sir. Now, you take this as a reflecting surface. Do you have an angle at which I can completely polarize the light? Do you have an angle theta p where I can completely polarize the light? That is Brewster's angle. If angle of incidence is theta p, angle of reflection is theta p. So now here what direction of propagation is left over? This will be left over on reflection, reflected wave. Right? This is the transmitted wave. So this theta p is the angle at which the light wave is completely polarized. This is polarizing angle. This is the angle of incidence at which the light wave is completely polarized. Theta p depends on mu. First point that you should remember. And this happens when reflected ray and refracted ray are mutually perpendicular. Condition for this to happen, reflected ray and refracted ray are mutually perpendicular. What are you telling me here? That means this angle is 90 degree. Are you trying to tell me if this is 90 minus theta p, this will again be theta p? Obviously, this is 90 minus theta p. This will be theta p because reflected and transmitted wave should be mutually perpendicular. That is the condition for total polarization to happen. That means sine of, this is mu refractive index, this is a 1 into sine theta p is mu into sine r. Which law did I apply?
That is law.
That is law. कौन है?
Snell's law.
हाँ? ये Faraday's law बंदा कौन है? नाम बोलो तेरा, घर आ जाऊंगा आज. You are telling me theta p. Now what will this be? What will this angle be? This is r. R plus theta p should be 90. So I will have sine of theta p is mu into sine r is 90 minus theta p. Sine 90 minus theta.
Cos theta.
Wonderful. Sine theta p cos theta p tan theta p is equal to mu. This is called Brewster's angle, that angle of incidence at which the wave is completely polarized due to reflection.
Or can we generalize it by mu of dense or by mu of rarer?
This is that medium, mu of the second medium upon mu of the first medium. Here I took air, so this is mu is 1. If not, mu of the second medium with respect to the first medium.
Okay, so
Call this mu to be mu of second medium upon mu of first medium. By the way, did you people ever wonder why polarized sunglasses are very costly? What decreases in polarized sunglasses?
So they reduce the glare.
The light coming straight, its intensity doesn't decrease. It seems the maximum strain we will have on a hot summer day is because of light reflected from the roads, buildings, or your surrounding. आप road पर जा रहे हो, your eye receives more strain because of this light entering in. So this light coming from the side should decrease. Its intensity should decrease. How? You are coating it with a material of refractive index mu such that tan theta p is mu. So once you have that coat, the light coming from the sides, its intensity will come down to half. So the strain in your eyes further decreases. So polarized sunglasses, you're not supposed to see the solar eclipse. Dangerously dangerous it is. Because solar eclipse you will not see from the side, right? You will see straight aiming towards the sun. Whole intensity will go into your eye. And what is solar eclipse? Intensity of sun's light goes down. Your iris protects the. Did I tell you about this? This is the lens, this is the retina. Parallel light rays come and converge on the focus, that is the retina. If whole of the suns, you watch the sun this way, the intensity of the sun rays will burn the retina. Fraction of a moment, you will lose your eyesight. What protects your eye then? There is something called iris, which is an involuntary muscle, which doesn't hear to the instructions of the brain. The moment the intensity of light increases, the iris will close down. So the intensity which enters inside is much lesser. Only that amount of intensity which your retina can bear. Can you give me a proof of this? If you ever walk from bright light into a dark room, first you can see nothing. Then immediately after 2-3 minutes, when your eye gets accustomed to the darkness, you are able to see. How does that happen? Once you go into a dark room, the retina and iris will adjust themselves in such a way so that the iris opens up. Greater intensity of light enters. Now you are able to see the people or inside the dark room. So that's the game with the iris. Now when you are watching the solar eclipse with naked eye, which is very dangerous, you are watching, intensity of light goes down because the moon comes on the way. When intensity goes down, your iris will open up. It's an involuntary muscle. It doesn't wait for instruction from the brain. It opens up. The moment it opens up, the sun rays with all intensities on the way. Moon will move. The sun rays with all intensity, when they fall on the retina, the eyesight is gone. That is a very dangerous thing. Hence, Polarized sunglasses, when you wear and try to see the solar eclipse, it is the most worst thing that we can ever do. Polarized sunglasses only decreases the intensity of light which comes from the surrounding. Straight Joe intensity RI, that will not be decreased. Is this clear to all?
Yes.
So by solar eclipse, you mean like in general also we can't look at the sun, right? Like
in general का solar eclipse का क्या होता है? Generalized solar eclipse, sun छिप जाता है कभी कभी.
no sun.
सोलर eclipse होता है भाई, मून comes on the way. थोड़ा बहुत ज्योग्राफी मुझे भी पता है, याद है मुझे. मून comes on the way. Other than that, there is no other solar eclipse.
What does polarization after a total reflection?
Pardon?
Total internal reflection का भी polarization होगा.
Total internal reflection का भी polarization होगा, yeah.
Okay. Is that उसमें कुछ special होगा? Will that be not polarized with the कुछ
Yes.
reflection?
When this condition is fulfilled, you are completely polarized in the way.
सर अगर रिफ्रैक्शन नहीं हो तो फिर कैसे पोलराइजेशन in total internal reflection? There is no, the light is not leaving anywhere, all the light is going back only. So
that will no. For some part is reflected, remaining part is absorbed by this. That will develop the temperature of that particular body.
total internal reflection में तो वैसा नहीं होता ना?
Total internal reflection में some part will be polarized, no doubt. In any form of reflection, some part is polarized. Maybe the polarized part may decrease. Proportion of the polarized part will decrease. But some polarization to hota hai. Maybe 0.1%, maybe 1%.
Sir, here R is the Brewster's angle, right?
Refracting angle. R is the angle of refraction.
Sir, so what is Brewster's angle?
Brewster's angle is theta p. Theta p is the angle of incidence at which the wave is completely polarized.
Okay, sir.
Second, polarization by double refraction. Polarization by double refraction. Double refraction. Main examples are quartz, calcite, and tourmaline. Splitting of refracted ray by the crystal. The phenomena is splitting of refracted ray. This splitting of refracted ray by the crystal leads to polarization. Right here, there are few things. Just draw this diagram for calcite. What happens here is, this is one prism, this is one prism. This is originally the light source. Right? This effectively goes straight. You are splitting this light signal. This is one signal, the other will go this way. The normal for this. This is called the E ray. This is called the E ray. What do you know? What do you mean by E? Extraordinary ray, which doesn't follow the laws of refraction. This is O ray. It is an ordinary ray which will follow the rules of refraction. The light ray appear to come from here. This is an extraordinary ray and this is the ordinary ray. This will be polarized like this. This will be polarized like this. So you are splitting the ray, splitting of the refracted ray by the crystal. Only few crystals exhibit this property. One is quartz, the other is calcite and tourmaline.
You said these are two separate prisms, right? That's it.
No, this is one single crystal.
Okay.
It is not biprism. I'll draw biprism next. First, I started drawing the biprism. Now, this is called Nicol prism. Nicol prism. Nicol prism is actually a combination of two crystals. One light ray comes this way and it is reflected, the other goes this way. Right? It technically comes this way and it comes out this way. The other goes straight. This is the incident light ray which is unpolarized. Right? This unpolarized light will come over here. Technically, this you would have collected here itself. And why did you create this barrier in between? And this barrier is made out of transparent cement. This barrier is made of transparent cement. It is called transparent cement. Right? Why? Because I want to collect one direction of polarized light ray here and the another direction of polarized light ray here, so that on two different sides I'll get. Previous crystal made came this way and it goes out, so I'll have one above, one below. Here I'm collecting the two polarized lights on two different directions. This is the ordinary ray, this is the extraordinary ray which goes undeflected. This is called Canada bulb. This is also called as Canada bulb. Transparent cement, different names for that. Can I rub the board?
So 1 minute.
Yes, Pastor.
So the black polarizer in the video you showed, what was that?
मतलब
नहीं मतलब वो sheet form में था क्या था वो?
It's a polarizer, light polarizer. Light का polarization करता है. It will permit light in only one direction.
Yes, I got that, but it wasn't one of the. So it's like a totally separate case, and it's not a prism or a crystal or anything.
अरे नहीं, that will come to it.
Okay.
Paul's law will show you that. Can I rub this?
Yes, sir.
Now, polarization by dichroism. Polarization by dichro. DICHROISM. Spelling ढंग से लिखो. Dichroism. Selective absorption. This is basically selective absorption. What happens? There are certain materials which will absorb light, but light of only one direction they will absorb. So what goes out is polarized. Write this down, I'll dictate the point. Can I?
Yes.
After some distance of penetration, after some distance of penetration, after some distance of penetration, one direction component of field vector, one direction component of field vector is completely absorbed and the light will contain only the perpendicular component.
Sir, could you repeat the entire statement once again?
After some distance of penetration, one direction component of field vector, is completely absorbed and the light will contain only the perpendicular component. The last two are polarization by scattering. Polarization by scattering. Scattered light gets polarized. Right? How do you see that? Here you have got scattered, unscattered light. Once it is scattered at this particular point, you will see polarized light here and polarized light in this direction. This is scattered in this medium. Right? This is polarized light. Right? Write down the first point. Can I dictate the point?
Yes, sir.
The degree of polarization, in scattered light, the degree of polarization in scattered light depends upon angle of scattering The degree of polarization in scattered light depends upon angle of scattering. Full stop. It is observed that when the angle of scattering is 90 degree, with respect to the incident light, when the angle of scattering is 90 degree with respect to the incident light, then the light ray is completely polarized.
So
Yes,
इसमें
sir.
both of these are polarized right now. दोनों से निकले दोनों ही polarized.
फिर से बोलो.
Both of these are polarized right now.
This is polarized at 90 degree. This need not be completely polarized.
Okay, fine.
When it is scattered at 90 degree, this light is completely polarized.
Okay.
The last point is Malus law. Brewster's angle and Malus law are the most exploited as far as polarization is concerned. Listen carefully. This is called a polarizer. This is unpolarized light. Intensity is directly proportional to amplitude square. Is everybody aware of this?
Yes.
Yes, sir.
Anybody with a doubt in this, raise your hand, I'll get it.
Chopped up.
Perfect. This is unpolarized light. In this direction, you will get, this is polarizer. This is called polarizer or analyzer. 1 second, I always get confused with these two. Which is, this is polarizer. This is called polarizer. Polarizer may what happens is you polarized in this direction. The slit is in this direction. You'll have only this. Now what you do is, 1 second, wait. Polarizer, analyzer, I hope I am not going wrong. Square of the cosine of the angle between the transmission of the analyzer and the plane of transmission of the polarizer. I have written polarizer here.
Yes, sir, that is the polarizer.
This is polarizer.
Yes, sir.
Yes,
Fine.
sir.
Fine. So now have a look at this particular orientation. I have another polar. Actually, both of them are polarizers, but the name given is
Yes, sir.
different so that you know which is which. Now this is another polarizer here. But what you do is you turn this way. You turn this way. This we will call as analyzer. Right? See, this is the way light is going. Now the analyzer is turned this way. I'll put it this way and I'll show you. This is the way light is going. Now analyzer is turned this way. So what component of the light falls on the polarizer along the slit? A cos theta.
Yes.
Great. When I draw this way, this component and this will be a sin theta. This will be a cos theta. A is the amplitude. Agreed? Because this angle is theta. Now what goes to the other side is only light of this direction of polarization. That means intensity will further go down. If this intensity is taken as I naught, this will be I naught cos square theta. Why so? Because you know I is directly proportional
Amplitude.
is equal to Ka square. I after passing through the polarization has become I naught by 2. This is important. Right? I naught by 2. Right? If not, you are taking this as I naught. I am okay. Call this as I naught. Right? Then call this I incident. I naught will be I incident by 2. I naught is I incident by 2. Right? Now, I after polarization will be equal to. This was originally I naught. I naught. I naught is equal to Ka square. Now Ka square. This becomes K into A cos theta whole square. Understand what's happening here? What component falls on this A cos theta? If intensity is directly proportional to K square, what component comes here? A cos theta. So now I will write K. Instead of A, I will write A cos theta. Is this step okay with all?
Yes, sir.
It will be K A square cos square theta. K square is I naught cos square theta. The polarized light intensity will be I naught. I naught is the incident light. If this is I, this will be I naught by 2. I by 2 rather. You are calling this I naught. This will be I naught cos square theta. Now understand one thing. You keep both the polarizer and the analyzer straight this way. Theta here becomes 0. Cos 0 is 1. So whole of this I naught will go this way. Agreed? Suppose I keep this way. Theta is how much?
90 degrees.
Cos 90 will be 0. Nothing
0.
will go to the other side. Now
Yes.
you recollect the video I showed to you in the start. I'll show you this once again. Take this down till here.
Sir, but IP equaling to I naught cos square theta is general formula, right?
Hey, no, this should be derived from here.
No,
Polarized
like,
light I naught cos square theta. You got it from here because of any analyzer.
sir, no, because like I naught equals to I by 2, right? So then how is that coming?
I naught equal
90.
to
I naught equaling to incident intensity of the
incident. You have got this and this both. One side is polarized.
Okay, got it, sir. Got it.
So are we gonna do diffraction today as well?
Let me see the time once, wait.
But it's 10:08.
Then probably we will have to set up another time. Tomorrow evening, how are you people placed? 7 o'clock.
So you were going to schedule a doubt lecture.
So tomorrow evening in the doubt lecture, first we'll finish diffraction. And then we'll have doubt lecture 1 we have been given even on Saturday. But we'll not wait till Saturday. Tomorrow evening, first we'll keep a doubt lecture. We'll finish diffraction. And then I'll take up the magnetism assignment doubts.
All right, sir. And sir, today GSP sir is gonna teach diffraction mostly. So should we attend that or not?
Attend it. अगर हो जाएगा the best thing.
All right, sir.
Don't waste time. If that saves time, we can directly go to polarization. I mean, we can directly go to what we call as magnetism doubt.
How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
Now you understood what he demonstrated.
Yes, sir.
This is all about polarization. Tomorrow evening's doubt lecture, if today diffraction is done, we save some time. Tomorrow evening's doubt lecture, I'll finish magnetism assignments. Depending on the time, we will go ahead with one more point. There are 2 to 3 soap bubble problems of surface tension and electrostatics which we need to solve.
So ARP son has done that. So
Fine.
problem problems. But electrostatic one, could you just give a problem or two?
Yeah, we'll deal with that in tomorrow's doubt lecture.
All right.
Right?
So we haven't done that. So can you do it from scratch?
Fine, no issue.
So when will you discuss EMI AC booklet?
EMI AC
Yes, sir.
booklet will be on Saturday's doubt lecture, which is given to us. First, we'll start with HCV, then we'll go to the booklet.
Okay.
So we are not having revision lectures, right? This week.
This week.
Are
They
we
sent you a schedule from Monday.
Yes, so they sent a schedule, but in the timetable nothing is written. And so we have-
They sent a new schedule. इसके बाद वाले Monday से शुरू हो रहा है.
So that day they came in our class.
यार आप लोग टाइम टेबल देख लो यार. अगले वीक का मंडे से they have given the schedule for crash course.
So will the revision lectures be online or offline?
Online, quite a few students have requested. Offline, some students are requested, so they'll be conducting both. One batch can sit at the center, the others can be online. And we will be somebody type vernier caliper screw gauge. We'll start with vernier caliper and screw gauge.
All right, so.
Sir, also one thing that I wanted to ask, we haven't yet been given the hard copy of the final lab modules. So if we go at
You
the
will have
center,
to
will
call
they
up
be available?
the center and fall behind them. I think hard copies have come. Which center are you from?
अंधेरी sir.
अंधेरी में आया हुआ है, तो क्यों नहीं
Okay.
दिया आपको?
नहीं
छीन
दिया.
लो जाकर. आया
नहीं
हुआ है.
दिया
नहीं
सर
नहीं दिया.
मैं भी गया था कुछ नहीं दिया
Call them up before going. Just don't travel blindly. Call them up, confirm. You'll have to go to the library and collect that.
Sir, we
Okay,
got
sir.
it. Thank you.
All right.
I typed something. I have a doubt in the verse. We can't use the direct result for the Q of capacitor now because it's time dependent. Naturally, Q is time dependent, current is also time dependent, but you can use Q is equal to Q naught into 1 minus e to the power minus t by tau will be universally varied.
So, but we derived that for a constant EMF now.
Yeah, but non-constant also you can use at that particular instant.
Sir, but in that I is equal to I naught, we think that I naught is at the maximum current, right? Which is epsilon naught by R. But at t is equal to 0, epsilon naught voltage of the battery is also 0.
So the differential equation becomes something different from what we derived.
But I think result will be the same. Let me see. Monday, tomorrow evening, while taking with doubts, I'll let you know.
So in the first question that you did, what will be the value of Q naught?
Maximum charge on it. You mean to say because it is time varying, Q naught becomes infinity, right?
Yes, sir.
Okay, understood. Then that will be hypothetical situation. But okay, if the problem is given, solve it the same. Because what they are trying to highlight is mutual inductance.
Okay, sir.
But d by dt is constant, no, yaar.
It is not, sir.
So 2t square दिया था आपने. So 2t
Then
4t बनता.
2t would make sense. The value 2t would make sense. Yet I'll see that. Tomorrow's doubt lecture, I'll let you know. Fine. Good day. Bye. Wish you all a happy Sunday.
Bye, sir.
Hi, sir. Thank you. Bye, sir. Thank you.